In this section, we talk about something called a contingency table. A contingency table, often called a two-way table, is a table made up of data from two different variables. For example, you'll see this table right here, which is indeed called a two-way table. You'll notice that it actually has two different variables at play. So the columns here looks like we're dealing with education, whereas the rows look like we're dealing with marital status. These two variables interchange to basically produce frequencies throughout the table. Let's talk about exactly what these frequencies are called. So if you'll notice, the education column variable there is associated with these four totals. For example, if I wanted to know the total number of people that did not graduate from high school, then that would be 27,891. So if you look very closely, each one of these has basically a total associated with it. Same thing on the other side. If you look over here, we have, looks like 6 different totals that are associated with all of the variables related to marital status. All of these frequencies, the ones that are basically around the outside and in the columns, are actually called marginal frequencies. So, for example, questions that I could ask would be something like, how many Americans were college graduates? What would you do? You would find the college graduate column, and you would find the total number that were college graduates, which would be 70,558. That number, 70,558, is a marginal frequency. It is a frequency that represents the total of one of the column variables. Similarly, if I asked how many Americans are separated, we'd be like, okay, well, now we're not in education, we're in marital status. So we go to the row variables, we find separated, which is right here, and we need to find the row total associated with it. So therefore, we have 4,648. Again, this is called a marginal frequency because it is a total of one of the variables, but this one would be the row variable. Okay, so that was marginal frequencies. So what about all the other numbers in the table? For example, you look at all of these numbers in here. These numbers I would characterize as frequencies that are in the body of the table instead of the outside columns, or let's say margins. That's a good way to put it, right? Marginal. But the ones that are more in the center of the table, these frequencies are actually called joint frequencies. I'll put an arrow here. These are called, actually I'll do it in green so I'm consistent. These are called joint frequencies. That is actually a pretty good name, only because joint usually means combined. Like marriage is a joint relationship, right? And the word join is actually in it. So it's two things combined. And if you think about it, if you look at any one of these values that we have here, for example, let's just look at our first value, 4803. What does that mean? Well, that is a frequency that represents the people that both were never married and did not graduate from high school. So it's a combo platter, basically, right? That's called a joint frequency. Okay, so looking at this third bullet that I just added, how many Americans were high school graduates and are divorced? Okay, so what are we looking at this time? We're basically looking at a scenario where we're going, note that in the first two of these, there was only one variable mentioned. One was college graduates, one was separated. Individual variables meaning basically that's a good signal that you're going to use a marginal frequency. Whereas this time, there's two variables mentioned with an and between them. So high school graduates and divorced. You could even say without the and, you could have said divorced high school graduates, whatever. It's a combination of both variables, which is a hint that if it's a combo, that it's going to be a joint frequency. So all we have to do basically is we have to find where these two variables overlap. So if we go over to the top and find high school graduates, we go to divorced along the side over here for a row, we go down and over, and we're going to find the one number that combines the both of them, which is going to be 7,725. This is a joint frequency because it combines two variables into the same frequency count. Okay, so moving on a little bit here. The title of this chapter is probability, which means that we don't necessarily want to know directly what the frequency of something occurring is. We'd rather know the probability of it occurring. So you'll notice that I've actually added the term probability over here with a question mark. What I mean by that is I'm not going to be asking how many Americans are college graduates. I'm going to be asking the probability that an American is a college graduate. I'm not going to be asking how many Americans are separated. I'm going to be asking what is the probability that Americans are separated, and so forth. In order to answer this, we're going to need to take a look at the one number that isn't highlighted in our table, our contingency table, and it is this number right here. So this is represented or often described as, in term, the table total. The table total represents all of the people, the total number of people in the entire questionnaire or study that you're dealing with. It also represents the sum of the columns and the row totals. This is a very important number because it represents the sample space. That number is the sample space of all the people in your study, which means when you go to do the probabilities, it should be the denominator of both the joint and marginal probabilities you're about to construct. For example, again, what if I wanted to know the probability that Americans are college graduates? So we already know what the total number of college graduates are. That's 70,558. That would end up being your numerator for your probability because that is the event that American is a college graduate. Our denominator is going to be the total in the sample space, which is going to be 191,884. If we do the calculations for that, we're going to get approximately 0.3677. So about 36.7%-ish of the Americans are college graduates. Notice again, though, what are you doing with a joint probability? You're finding the total of people that are American, of total number of Americans that are college graduates, which we determined was 70,558, and we're taking that out of the table total. Moving to the next one. We have the probability that Americans are separated. Well, again, what are we looking at? We want to go to our separated column. We want to find how many there are. Well, we determined that was 4,648. The event that they are separated is going to be our numerator. And our sample space, again, is going to be our denominator, which is 191,884. Okay, calculating this, we get a much smaller probability of 0.0242. Okay, lastly, what if we want to find the probability that Americans were both high school graduates and divorced? Okay, very similar situation, except now we're dealing with a joint probability. So just like we did last time, we're finding high school graduates. Remember, we went to divorce. Let me get rid of this. And then we found the number 7725. So that is, again, going to be your numerator. We're then going to take that 7725 and we're going to take it out of the table total, which is 191,884. Okay, so this is going to give us a probability of 0.0403 after some calculations. Now, be aware that sometimes students will struggle with the joint probabilities. They're okay with the marginals usually, but the joint probabilities cause a little bit of pain for students. Why? So if we go and find that number again, 7725 in our chart, remember that was the crossing high school graduate and divorced. You'll notice that, of course, you know now that you're supposed to use this as the denominator, but realize that there are actually two other totals associated with 7725. It's the column total and the row total. The most common mistake students make is they will literally take 7725 and divide by one of these instead. Just realize all marginal and joint probabilities will always be taken out of the table total. Try to remember that and you will avoid those mistakes. Okay, let's try another example just to give a different perspective. It says the table shows the results of a survey that asked 1,048 U.S. adults whether they supported or opposed a special tax on junk food. That sounds terrible. Either way, what you see here is another contingency table. It has two variables. It looks like birth gender is here. And we have stance, we'll call it. Stance on tax. Support, oppose, unsure. Okay, first question. Find the probability that an adult in the survey is female. Okay, it looks like there's no and involved with this. They're only asking about one variable. This implies that we are dealing with a marginal probability. So what do? We need to, first of all, we know the denominator. We need to locate the table total, which is right here. So our denominator is going to be 1048. Our numerator, therefore, we need to find the event that a person or an adult in this study is female. So we find female, and we need to find how many there are, and it looks like 555 will be what you get. We're just going to skip the decimal version for now and just leave it as a fraction. How about find the probability that an adult in the survey is unsure of whether they stand on the tax? Well, again, they're only asking about one variable, which means we're implying that this is going to be a marginal probability. But notice that it's not the variable it was before. It wasn't birth gender, so it's the stance on the tax, which means we're switching from a row variable to a column variable. Specifically, we're looking for the unsure, and more like the total amount of unsure. So we're going to, again, out of our 1048, we need to take the total amount that are unsure and get 27 out of 1048. Okay, last one. Find the probability that an adult is male and opposes the tax on junk food. Okay, so they changed things up on you here. They've basically, well, first of all, you can see they use the word and, in which they have two variables. We have birth gender and their stance on the tax, which means this is strictly a joint probability. So again, I'll do a little summary over here. This is marginal. Both of these are marginal, and then this one is joint. But the good news is, I always like to clarify what they are. Probably not going to ask you what they are on an exam per se, but it's nice to be able to locate which type it is so that you can look at it in the table in the proper way. But no matter whether it's marginal or joint, you've already been shown that 1048 must be the denominator because that's the sample space of all the adults in the study. In this case, it's a survey. But this time, we have a joint probability, which means we're going to be in the table in order to find what we're looking for. So which one is it? We're looking at male and oppose. So if we bring them together, we're going to get 325 as our value here. Wrong color, but that's okay. 325. And this will end up being our probability. Okay, so let's bring up one more important concept. It's basically a different type of question that you could be asked. You'll notice that basically all I did was, to start this, was I took this one and brought it down here. But what I'm going to do is I'm going to change it to letter D, and I'm going to change one word. I'm going to change this and to the word or. My hope is as soon as you saw this word or, then big light bulb went off in your head. Because remember, anytime we have two events that we're dealing with connected by the word or, we're dealing with the addition rule, which means now we have a little bit more to think about. For example, we have two addition rules. One of them is for disjoint events, and one of them is for joint events. Well, if you look at these two variables, male and oppose, we clearly have 325 that fall into both, which means there is an overlap. If there's an overlap, we're dealing with joint sets or joint events, so therefore we must use the larger addition rule. To make life easier, let's call this event M for being male. We'll call this O for opposing the tax. So we're going to be doing the probability of M or O is equal to the sum of the two singular probabilities minus their overlap, which is M and O. So our only task here is we just need to find each one of these probabilities. Now, we'll start with the probability of male. What's really interesting about the probability of male is that it's very similar to this question, the probability of female, which means that the probability of male here is actually a marginal probability. Hopefully you can see kind of where this is going. Just like this guy here is the probability of oppose. Well, we already covered the probability of unsure, and that was a marginal probability. So the first two probabilities in the addition rule scenario are just marginal probabilities that you just learned how to find. So let's do them really quick. We have the probability of male, which is going to be out of our 1048, how many of them are male? Well, it looks like 493. Out of our 1048 for the probability of oppose, how many of them oppose? Well, 625. So we're adding those together. Now, for whatever it's worth, if we actually added these two together, we would get more than 1048, which doesn't make any sense. So if you had made a mistake in this scenario and did the wrong addition rule, you would have gotten a very weird answer, a probability bigger than 1, which you know you can't get. So what do we need to do? We need to subtract the probability of male and oppose. But again, male and oppose, look at this over here. Didn't we already find the probability of male and oppose? We did. It was a joint probability. So our last probability is a joint probability, and yes, we already found it. 1048, we have male and oppose, which will put us at 325 out of 1048. So if we basically put these together and do a little bit of subtraction, then we're going to get 793 out of 1048. And just because I already had it, I'll tell you that that is 0.7567. Note on exams, I accept either one of these as your solution to the problem. So the real thing is here is that students sometimes get stressed, and you probably did when you saw that I all of a sudden changed a contingency problem into an addition rule problem. I get that. But the reality is, if you're doing an addition rule problem, what are you doing? All you're doing is taking the sum of two marginals and subtracting a joint probability. That shouldn't be too tough. If you understood everything that's up here pretty well, then that means you're going to understand how to put them all together, the three of them, in order to get your resulting probability.